So as we discussed in Physics 116 for most of you, or you're familiar with, uh, molecules are sometimes modeled as as a series of compound oscillators, wherein the interaction between the atoms within the molecule are modeled as elastic forces. So that means uh, we're now going to consider not only the translational motion of particles, but also the vibrational motion of the particles. So remember that when you increase the motion, when you increase the temperature of your system, of your molecule, okay, the number of degrees of freedom increases. So that means additional kinds of motion emerge. So aside from translational motion along X, Y, Z, the particle will start to rotate as well as to vibrate like this. So as a simple model, we're going to consider a one-dimensional triatomic molecule. Okay, this is a three-particle system connected like this. So unlike our discussion before, wherein the end particles are attached to a fixed, this time these particles are not attached to a fixed point. They are only attached to a central point. Okay, so an example of which is a carbon dioxide molecule. Okay, typically the central atom is heavier than is of different mass than the end atoms. Okay, so let's call this atom number 1. This is atom number 2, and this is atom number 3. Okay, the spring constants are K and K. So these are considered to be the same interaction because we're dealing with the same pair of atoms. Okay, as discussed before, the two end particles are bound to the central particle of mass capital M. The end particles have the same mass, small m. Okay, so from here, we can now define the following displacements with respect to their respective equilibrium position. Let's call this x1, x2, and x3. Okay, so now let's compute for the equations of motion. As you will notice here, we have three particles, so therefore we expect that we will have three equations of motion. Okay, so let's start with the computation of kinetic energy. Can anyone tell me the kinetic energy of the system? Anyone? Okay. Kinetic energy of the system is of course given by 1/2 m x1 dot squared plus 1/2 capital M x2 dot squared plus 1/2 small m x3 dot squared. Okay, and the potential energy would be the potential energy associated with the two springs. So this is now equal to U equals 1/2 K times the net displacement or the amount of compression or decompression of this spring, which is a difference of the difference between x2 and x1 squared plus the potential energy associated with this particle. So that's 1/2 k x3 minus x2 squared. Okay, so therefore, the Lagrangian can now be rewritten as follows. The Lagrangian, which is the difference between kinetic and potential energy, is now equal to 1/2 m times x1 dot squared plus x3 dot squared plus 1/2 capital M x2 dot squared minus 1/2 k times x2 minus x1 squared plus x3 minus x2 squared. So as you will notice, this Lagrangian is a function of x1, x2, x3, x1 dot, x2 dot, and x3 dot, and all are functions of time, which suggests that there are 3 degrees of freedom, which is what we expect earlier. Okay, as an exercise, which you can do later, determine the equation of motion given this Lagrangian. Okay, so I'm going to skip ahead to the equation of motion. So by solving the Euler-Lagrange equation, okay, we are now going to write the resulting equations of motion. Okay, so the equations of motion are as follows. The first equation of motion associated with x1 would be m x1 double dot. This is equal to negative k times x2 or negative k minus x1 minus x2. Second equation is capital M x2. This is equal to k times x1 minus 2 x2 plus x3. And lastly, m x3 double dot is equal to k times x2 minus x3. Okay, so if we're going to rearrange this, we can rearrange this as follows. So this is m x1 double dot plus k x1, and then this is minus k x2, and then this is equal to 0. Equation number 2. So as you will notice that I am aligning some terms. So this is x1 plus m x2 double dot plus 2 k x2 minus k x3 equals 0. And lastly, this is negative k x2 plus m x3 double dot plus k x3 equals 0. I did this so that it's easier for us to put this in matrix form later. Now if for example, if we assume an oscillating solution given by x1, a1 e to the I omega t, x2 as a2 e to the I omega t, and x3 as a3 e to the I omega t. So that means what? That means x1 double dot is negative omega squared. A1 e to the I omega t. Same goes with x2 and x3. So substituting that in this equation, we can now rewrite this as follows. Okay, so this becomes negative omega squared m, m a1 this becomes a1, this becomes a2, similarly this becomes a1, a2, then k a3 here, and then this one becomes negative capital M omega squared. And then lastly, we write this as follows. This is minus k a2 minus m omega squared a3, and this is k a3. Okay, so therefore we can now rewrite this in matrix form. Okay, in matrix form, this becomes a 3 by 3 matrix. Okay, so the first row would be k minus m omega squared, so this one. This one is this, and then negative k, and then 0. This is a1, a2, and a3 equals 0. So the second row becomes negative k, then 2k minus capital M omega squared. And then lastly would be negative k. And then the third row would be 0, negative k, and then k minus m omega squared. So this of the form k a equals 0, and this can be solved when we set the solution would be, if we get the determinant of k n equated to 0.